Okay, cool. So let me introduce our invited speaker here today. So our invited speaker is Dr. Emilie Jué. So thank you, Emilie, for joining us today. Dr. Emilie Jué is an associate of National Institute of Standards and Technology, NIST, and she is also a research associate at the University of Colorado Boulder. She obtained her PhD from the University of Grenoble with SpinTech in 2013. After her PhD, she did a postdoc at NIST Boulder, where she is currently working. And her current research focuses on spintronic devices for neuromorphic applications at the hardware level. She will talk today about magnetic Josephson junctions for artificial synapses. Emilie, feel free to share your slides.
Okay. Can you see my slide and can you hear me correctly?
Yes.
And here is my video. Okay, well, thanks for this introduction, Saima. And to start, I would like to thank the organizer of this conference for inviting me to give this talk. It's my pleasure to be here. And today I'm going to present the works that we did at NIST on magnetic Josephson junction for artificial synapses. So before I start, I would like to acknowledge all the people who contributed to this work. And more specifically, I'd like to point out that the device I'm going to present here the idea of the device has been proposed by Stephen Rosek. And a lot of the results that I'm going to present here has been obtained by Mike Schneider. So here is the outline of my talk. So I'm going to start with an introduction on neural networks, and I'm going to give you some motivation about why we're interested in developing hardware for AI at the device level. In a second part, I'm going to present our device that we developed at NIST. It is a magnetic Josephson junction. I'm going to show you that we can use it as an artificial synapse. And in the last part of my talk, I'm going to show how we can use this magnetic Josephson junction inside a neural network, and I will show what type of application we can do with it. Okay, let's start with the introduction. So here I'm talking about hardware for AI. And when I'm talking about AI here, I'm thinking about bio-inspired neural networks. The principle of a bio-inspired neural network consists in creating a network of neurons that are connected by synapses. The role of the synapse is to adjust the strength of the connection between the neurons. So in our brain, the synapse is responsible of the plasticity, which is the capability that we have to learn and to modify the memory. So in a simplified picture, if we want to do a neural network, we need a presynaptic neuron that's going to emit a spike. This spike is going to be transferred to a synapse. This synapse will modify the amplitude of the spike by applying some synaptic weight. And then this spike is going to be transferred to a postsynaptic neuron, which is going to sum up all the incoming signals. And based on that, it's going to decide if yes or no, it wants to trigger another spike. So here is a very simplified picture, but just with this simplified picture, there are many things we can do. And all these actions can be simulated at the software level through algorithms. And in fact, all the applications of AI that you use every day are made at the software level. Here, I'm not going to go into the details, but I just wanted to point out that there are a lot of applications that you use every day, such as, if I give the name Apple, Google, Microsoft, Amazon, or Facebook, those are big names that we all know, and we use those applications every day. And they're all using neural network at the software level to complete their task. Neural network at the software level is also used for self-driving cars. It's used to assist medical diagnosis, also used for applications that we are less aware of, such as drug design, farming, beer brewing, and so on and so on. So here's really a lot of things we can do. And basically, we can see that the progress in terms of software algorithm in the last decade has allowed many exciting applications. However, the increase in performance that we've seen also come with a significant demand in terms of training. So on this graph that I'm showing here, I'm showing the amount of compute that we need to train a single model as a function of the years. And what we can see here is that over the last decade, the training demand has been doubling every 3 months. To put that in perspective, it is about 7 times the exponential rates that we observed with the Moore's law. So the reason of this significant change between this first era and the modern era is that around 2012, people started developing new hardware that helps algorithms run more efficiently. These new hardware are digital circuits, such as GPU or TPU, which stands for graphical or tensor processor units. Here, I don't want to go into any details, but basically, those digital circuits are often called hardware for AI, but their function is still to perform digital logic and run software algorithms. However, as you can imagine, the high training demand of this software algorithm has a cost. It has a cost in time of energy, in terms of time, and all of that has a financial cost too. For example, it has been estimated that the cost in computing power that we need to replicate the experiment reported in the AlphaGo Zero paper is about $35 million for 40 days of training. So that just gives you an idea of what we're talking about right here. So one solution that is proposed to reduce this cost is to develop hardware for AI at the device level, because it has the potential for fast and low energy computing. So to make hardware for AI at the device level, we need to be able to recreate each building blocks of a bio-inspired network at the device level. So as we've seen earlier, it will include the neurons, so as a signal source, but also as signal analysis. It will include the synapse, which allows to apply some synaptic weight on the signal. But here we're speaking about hardware, which means that we also have to take into account the connectic, and it's also important for us to recreate the axon, which is this line that allows to propagate the signal. So it turns out that all these building blocks can be made at the device level with Josephson junctions. So don't worry too much. If you don't know what is a Josephson junction, I will explain the basic concepts that you need to know. So why do we want to work with Josephson junctions? We all do magnetism, so why are we moving to, why am I moving to superconductivity here? Well, it turns out that the Josephson junction is naturally a good candidate for neuromorphic computing. For example, in the same way that the brain can transfer information with quantized pulses, the Josephson junction can naturally emit quantized spikes that we call single flux quantums. On another hand, the brain transmits information on long distance through the axons that are lossless line. In the Josephson junction world, the spikes can also be transmitted on long distance with transmission lines. As I mentioned before, the capability to modify the memory is called the plasticity, and in the brain, it is achieved through the synapses. In this talk, I'm going to show that we can use a magnetic Josephson junction to reproduce this synaptic behavior. In terms of number, the brain has about 100 billion neurons, whereas according to the current state of the art, a chip can include about 1 million Josephson junctions. So here we are 5 orders of magnitude less than for the brain, but it is a pretty decent place to start. And finally, the speed of the brain is about 100 Hertz, whereas the Josephson junction can spike 1 billion times faster than the brain. So here we start to get a good feeling on why this device is interesting. So let me introduce now our device, which is a magnetic Josephson junction. Before we dive into the magnetic aspect of the device, I just would like to explain a few basic properties of the Josephson junction itself. A Josephson junction consists in two superconductors that are separated by a non-superconducting barrier. It is usually characterized by its IV curve that shows the voltage as a function of the current that we send through the junction. So we're going to see a lot of these curves in this presentation, so I'm going to describe it a little bit. So they typically have two regimes. When the current is below a critical value that we call the critical current, the junction operates in a superconducting state. However, when the current is above the critical current, the device starts emitting single flux quantum pulses, which are quantized spikes. In this regime, the DC voltage that we measure is the time average value of the spiking state of the device. The Josephson junction that we are studying here is a little bit special because it is a magnetic Josephson junction, meaning that the barrier is composed of magnetic clusters inside the dielectric. Note that for a very long time, people were actually very reluctant to add magnetism material in superconducting device because the magnetism tends to kill the superconductivity. However, if we use it well, we can actually have access to some interesting properties. Here, more specifically, we're going to see that the natural spiking behavior from the Josephson junction and the plasticity from the magnetic clusters can give rise to synaptic behaviors. So let's have a closer look at the magnetic aspect of the magnetic Josephson junction. Here is a barrier. So in this case, the barrier consists, in our device, the barrier consists of clusters of manganese inside a matrix of silicium. And this barrier is sandwiched between two layers of niobium, which is a superconducting material. To make the cluster, we deposit a thin film with multi-layers of silicon and manganese by sputter deposition, and we anneal it at 400 Celsius for 10 minutes. The device is then processed with optical lithography in the shape of pillars with a diameter of 1 to 10 micrometers. So we look at the magnetic properties of the sample with a squid magnetometer. On this graph, I show the magnetic moment as a function of the temperature when the temperature is decreased from room temperature to 4 Kelvin. The temperature corresponding to the maximum magnetic moment is called the blocking temperature. Above this temperature, the clusters are in a superparamagnetic state, meaning that the orientation of their magnetization is unstable due to the high thermal energy. Below the blocking temperature, the magnetization of the cluster is blocked in a fixed direction. And we can use this property to reset the orientation of the magnetic clusters with the temperature. So this is done by heating the sample and cool it down in the absence or in the presence of a magnetic field. So we now repeat the measurements in presence of a magnetic field. And in this case, we observe that the magnetic moment at low temperature increases with the value of the magnetic field, which means that we are ordering the clusters magnetically. Here, the minimum magnetic moments correspond to a disordered state with the cluster magnetization pointing in random directions, whereas a high magnetic moment corresponds to a highly ordered state where the magnetization of the clusters are all aligned. So the main takeaway of this slide is that the magnetic order of the device can be controlled with the temperature. So to measure the device electrically, we place the sample inside a probe station that is operated at 4K, and we use two ground signal ground probes to apply a current and measure the DC voltage through the device. By doing so, we can measure the IV curves of the device when the sample is in a disordered or in an ordered state. Interestingly, we see that the critical current can be tuned with the magnetic order of the device. Indeed, we observe that a magnetically disordered device has a much higher critical current than when it is magnetically ordered. To put this result in perspective, I can make a simple comparison with a device that you all know, which is a magnetic tunnel junction. In a magnetic tunnel junction, even with a high TMR, the change of resistance is rarely more than a factor 2 between the parallel and the anti-parallel state. Here, with the magnetic Josephson junction, we observe a change of critical current, which is 2 orders of magnitude between the disordered and the ordered state. So this change that we observe here is really significant, and we're going to use it. Okay, so here the main takeaway is that the critical current can be tuned with a magnetic order. For this work, we're going to use 2 different methods to control the magnetic order of the device. The first one is the one that I described before and consists in heating the system above the blocking temperature and letting it cool down in the presence or in the absence of a magnetic field in order to obtain an ordered or a disordered state. For the second method, we keep the sample at 4K at the whole time, but we apply short current pulses through the device in the presence or in the absence of a magnetic field. The first method is easy to implement, but it is also very slow. It is not easily compatible with neuromorphic applications since we need to vary the temperature. On another hand, the second method is more invasive and more complex to set up, but it has the advantage of being fast and it is compatible with neuromorphic application because in this case, the ordering properties can be controlled while maintaining the sample at 4K for the whole time. So using this second method of ordering with fast electrical pulses, we look at the critical current as a function of the number of pulses that are applied through the junction. So here, our pulses are roughly 11 picojoule of energy per pulse. So here we can see that we can tune in a fine way the magnetic order of the device with the number of pulses, which allows to tune the critical current. So more importantly, what we see is that in addition to obtaining a low and a high critical current, as observed before, we also have access to intermediate values of the critical current in such a way that we have a quasi-analog variation of the critical current. So this result is important because it is this property that will allow us to use the device as a synapse by using the critical current as a synaptic weight. So I'm going to describe this part a little bit more later. So finally, before I move on, I would like to point out that the physics that allows to order the cluster with the electrical pulses is not really understood for now. Indeed, even if all the energy of the current pulses went directly into heating the junction, we would expect a temperature increase of roughly 15 Kelvin, which is way below the blocking temperature that we have, which is 52 Kelvin for this device. So here there is some physics that we don't understand and that we would like to explore in the future. Okay, so I told you earlier that hardware for AI at the device level have the potential for low energy computation. So let's look at the energy that we need for this device. Here we dissociate 2 types of energy. So training energy, which corresponds to the energy of the pulse that we need to modify the magnetic order, and which is directly related to the magnetic anisotropy of the clusters. We also have the spiking energy, which is the energy that we need to emit a single flux quantum pulse. On this graph, I show the pulse energy as a function of the area of the device. Here we see that the energy of the device is scalable with the size of the device. And we can see that for our lowest size or smallest devices, the energy can be as low as 3 attojoule for the training energy and 10 zeptojoule for the spiking energy. So here we're speaking about very, very small energy. To put that in perspective, if I compare it with the energy that we need with the brain, the brain needs about 10 femtojoule to emit a spike. And even if we consider the effective cooling overhead that we need to keep the device at 4K, our device can still be more efficient than the human brain. So that is a very positive result. So here I've shown several promising results, but I should also point out that we have several points. There are several points that we don't understand or that we would like to optimize. So for example, we don't really understand the mechanism that allows to tune the magnetic order with the electrical pulses. On another hand, we would like to study the relation between the number of accessible values of critical current versus the number of clusters in the device. Additionally, I told you that the training energy is related to the magnetic anisotropy of the clusters, meaning that tuning the cluster properties should allow to improve the training energy. So for all these reasons, what we would like to do now is to tune the clusters properties to understand better the physics of the device and to optimize its properties. Unfortunately, it turns out that the silicon manganese is not the best material to do some accurate tuning of the cluster's properties due to its deposition process. So for this reason, we're going to study another material system than the silicon manganese, and a material system that would be that we could tune in a fine way, where we could tune the cluster properties in a fine way. So to do that, we worked with the Karlsruhe Institute for Technology in Germany, who own a custom deposition system, which allows them to do a very fine tuning of cluster properties. So here we're going to study a new system, which is where the sample is composed of a barrier of germanium and iron. So we have cluster of iron inside a matrix of germanium. And this barrier is still in sandwich between two layers of niobium. The sample is deposited here with a size-selective, low-energy nanoparticle deposition system. And so with that, they can really control a lot of properties of the clusters. In our case, we work with the following properties. I would like to point out that to date, the magnetic Josephson junction has never been demonstrated in any other system than in silicon manganese. Therefore, our initial goal is simply to demonstrate that the synaptic behavior can also be obtained with this new system, which is with a germanium iron barrier. As a reminder, to demonstrate that we can use the device as a synapse, we need to demonstrate that the critical current depends on the magnetic order, and that we have a quasi-analog variation of the critical current with electric pulses. So using the cool-down device method to magnetically order or disorder the device, we see that the critical current in the ordered states that you can see in blue here is about 100 times smaller than in the disordered state in red. So these simple measurements fulfills our first requirement that the critical current must depend on the magnetic order to act as a synapse. I also would like to point out that here our current values are much smaller than what we had with silicon manganese, but we still maintain 2 orders of magnitude between for the critical current between the order and disordered state. Okay, so we now want to see if we can obtain a quasi-analog variation of the critical current by applying current pulses. So by using the second method of ordering with electrical pulses, we now measure the critical current as a function of the number of pulses for pulses that are, again, about 11 picojoule per pulse. Here again, we are able to demonstrate that we can reach intermediate states of the critical current with the number of pulses. So these results fulfills our second requirement for the MJJ to behave as a synapse. That is that the critical current can be varied in a quasi-analog way with current pulses. So therefore, we can conclude that the the device with germanium iron bar here can be used as a synaptic device. So this result is exciting for us, first because it's the first time that it is made in another system than silicon manganese, but also because with this device, we should be able to do a fine tuning of the cluster properties, which means that it's going to allow us to study the physics of the device. This work also opened up some new options to optimize materials for synaptic devices in neuromorphic applications. And I would like to now move to to the last part of this talk, where I'm going to show how we can use the synaptic behavior of the magnetic Josephson junction in neuromorphic applications. So for that, we can build a basic neuromorphic cell with Josephson junction and magnetic Josephson junctions. So I'm not going to go into the detail of this circuit, but in a simple way, the cell is divided in 3 parts. We have a presynaptic neuron that generates the initial spike. We have a synapse, which is composed of the magnetic Josephson junction, and that is used to apply the synaptic weight. And we have a postsynaptic neuron, which makes the decision to trigger or not an output spike based on the incoming signal. So far, I've been a little bit vague on the way the neuron makes the decision to trigger or not an output spike based on the input. So the magic of the operation lies in the F in front of the sum. This little F is called the activation function. And the activation function is basically the function that determines if the output neural network should be a yes or a no. A very common activation function used in a lot of software neural network is called the sigmoid function and have the following shape. So here we use WR-SPICE, which is a circuit level time domain simulation tool to simulate our neuromorphic cell with the magnetic Josephson junction. More specifically, we look at the variation of the critical current of the postsynaptic neuron as a function of the initial critical current of the magnetic Josephson junction. And by doing so, we can demonstrate we demonstrate that we can obtain a sigmoidal function where the variable is the critical current of the magnetic Josephson junction. So we're very happy about this result. To verify that our simulation results are relevant, we also fabricate the neuromorphic cell and compare it with our simulations. So for that, we work with the MIT Lincoln Lab to build our neuromorphic cell, where the magnetic Josephson junction here is replaced by 4 fixed Josephson junctions with different critical current. The figure here is an optical photo of the circuit from the foundry. Interestingly, the measurement of the circuit shows a very good match of the simulations and the experimental data within the process error margins. So this result here is important for us because it shows that we can trust our simulations and that we can trust our numbers. Finally, I would like to show an example where we use our neuromorphic cell with the magnetic Josephson junction inside the neural network. Here we simulate a 9-pixel classifier for high-speed recognition. The goal is to train the network to recognize the letter Z, V, or N. The incoming image is decomposed in a column vector, which determines if the presynaptic neuron will fire or not, if it will fire a spike or not. After we let the network do its magic, we obtain an output spike for the letter Z, but we don't obtain anything for the letter V and N. So here we can see that the network was able to recognize the letter Z. The network is also robust to a 1 pixel of input noise. For example, if we change only the first pixel here from 1 to 0, the system will still fire a spike only for the letter Z, because it is the closest from the 3 letters. We can analyze all the images of Z, V, and N with any 1 pixel input noise, and every time the network will return a spike only for the correct letter. With this network, we were able to demonstrate that we have 100% accuracy of recognition at a frequency of 125 gigahertz, which is very fast. Although this network is very simple, it shows that the magnetic Josephson junction can be used at the synapse as a synapse in a neuromorphic network. So here this work has been made with simulations, but we hope to do them. We hope to reproduce this network experimentally in the near future. Before I conclude my talk, let's compare the performance of the magnetic Josephson junction with other technologies. On this graph from Nikonov and Young, they show the relative relation between the energy and the delay for different emerging technology to reproduce the LINET model, which is an example of convolutional neural network. So we can make a very rough estimation to see how our device performs compared to other technology. So very roughly, what we can see is that we have seen that our neural network, based on the magnetic Josephson junction, can operate at 125 gigahertz. So this corresponds to a delay of 8 picoseconds. On the other hand, the spiking energy of the magnetic Josephson junction is about 100 zeptojoules. And the LINET circuits require 13 million elements, which correspond to a total energy of 1 picojoule. So finally, if we take into account the cooling power that we need to operate the circuit at 4K, so total energy to reproduce the LINET model with the magnetic Josephson junction is estimated to be roughly 1 nanojoule. If I compare this result with the other technology, here is where our device should be. So obviously, so there is a big caveat here. It is not a very fair comparison because our numbers are obtained with a very small circuit compared to the very big circuit that you need for LINET. However, this is a very good result with some preliminary work. And we still have several decades of space in terms of delays to make this device competitive. So we think that those results are very encouraging. So with that, I would like to conclude my talk. So here I have shown that the magnetic Josephson junction is a hybrid magnetic superconducting device, which can be used as artificial synapses by using its critical current with the magnetic order. So this device has several advantages. It is naturally spiking. It is fast and it uses low energy. Recently, we have also demonstrated that the synaptic properties are also observed in a new material system that provide more options to tune the cluster properties. So we think that these results will open up new options to study the physics of the device, but also to optimize new materials for neuromorphic applications. And finally, I've shown that the magnetic Josephson junction can be included in a neuromorphic circuit. And more specifically, we demonstrated that we can obtain an activation function with a circuit based on magnetic Josephson junction. And it can be used to build a high-speed recognition network. With that, I thank you for your attention.
Thank you very much, Emilie. I'd like to open the floor for questions. Remember to you can use the reactions and raise hand, and we'll unmute you. Right. Okay, so Sarah MJJ.
Hi. Great talk. Very interested in what is the physics that's causing the clusters to orient with the pulses. Have you looked at it in terms of maybe the pulses are just destabilizing the clusters and you're just using the field to get to the ground state? So if you looked at the field amplitude or temperature or cluster size effects?
So that's definitely on my list, and yeah, there's a lot of things like that we want to do, like by varying the field, varying like the amplitude, the length of the pulses, varying the amplitude of the pulses, and really see what is the most important here. We have so much work to do with this device that I haven't done that yet, but that's definitely one of the things I want to do next.
Okay, great.
Sima, you have a question?
Hi, Emilie. Great talk. Thank you. So I have one question. So in slide 21, you showed that you have to apply like 10 to the power 5 pulses to like close to million pulses to change the critical current. So I was wondering, what's the stability of this tunnel junctions or Josephson junctions are?
You mean like if it's going to stay in that state after I apply the pulses?
No, I'm just more like where does it break down? Like how many cycle you can.
Oh yeah. Oh, I'm glad you asked this question. I totally wanted to mention that. Actually, those devices are way more robust. That's what you can have with a tunnel junction, a magnetic tunnel junction. I mean, if you look at even like the previous, let me just go back a little bit higher. Like in this type of like here, I'm applying like 1 milliamp through my device, right? So that's not something that I can even hope. So with the magnetic tunnel junction, so they're very robust. So far, I imagine that if I start applying way too much current, it's going to be a problem. But like applying a bunch of pulses has not been a problem so far. I think like I should mostly have to be careful not applying too much energy at once.
Mm-hmm, mm-hmm. Great. Okay, thank you. One other question about the speed. So you talked about this junction can operate about like 8 picosecond. So in your experiment, like from your experimental experience, do you expect them to operate in the picoseconds, or it's?
Actually, I do. If again, let's just move to that slide. Sorry, I'm very bad with navigating through these things. So this slide for me is key because that's an experimental validation that the numbers that we're bringing up here are actually not, we can trust them. And like one thing I really should insist on is WR-SPICE is time domain simulation. So like it's not some random values that we put here. Like we really like put some all the properties that we have of the device, of like all the connectic in between, and a lot of things. And we kind of hope that 125 gigahertz is actually reasonable. We think that when we're going to do it experimentally, we're probably going to work we're going on purpose to tune the properties to work at a slower speed because it's easier to measure. But we really think that we can reach this speed.
Okay. Thank you, Emilie. And again, thanks for the great talk.
Thank you.